The vast majority of software development is performed on existing systems. Software maintenance and evolution are the primary components of the system's total budget. Software changes can be split into four broad categories. The first are corrective changes, which fix defects and account for 21% of all changes. 25% of changes are adaptive. That is, they help the system work to interoperate with external changes that modify its execution context. Perfective changes, which add or modify functionality, comprise of 50% of all program changes. Finally, preventative changes improve program structure and account for only 4% of program changes, although these changes have an outsized effect on enabling the other kinds of changes to be successful. Software maintenance is hard because over time, code can become complex and unstructured, sometimes due to poor initial design, but more commonly due to a lack of preventative maintenance or churn as the project is evolved. Maintenance challenges can also be exacerbated when software engineers lack sufficient domain or historical knowledge about their projects. Finally, time pressures often push quick fixes over comprehensive ones, which can degrade the quality of the system. As code evolves, it often degrades to the point where fixing bugs and adding new features becomes harder than it used to be. Code smells are negative traits that long-lived systems often exhibit within their code. Martin Fowler defined 5 main types of smells. The first is bloaters. These encompass smells whereby the size of the program elements make them harder to understand or change. Really long methods, large classes, and methods that have long parameter lists are all examples of bloaters, right? Because when you have a method that is 100 lines long or a several hundred line long class, it becomes hard to just take a look at that class or method and really understand concretely about what it's doing. OO abusers are a class of smells that arise when object-oriented design is not leveraged. For instance, if we're using switch statements, or we have refused bequest where some subtypes don't honor other types' expectations, we have smells that indicate poor object-oriented design. Change preventers are a class of smells that make it harder to evolve your code. These include divergent changes, where you'll have to make the same change in multiple different parts of your system, or shotgun surgery, where you have a change that's spread across the breadth of your system. Dispensables are smells that capture unnecessary complexity in the code. For instance, if you have duplicate code, dead code, or you have speculative generality. Right? We've mentioned before that premature optimization can cause all kinds of problems, and the same thing happens when we have premature extensibility. So every time we add a new abstraction to our system, it can become harder to understand, and speculative generality really tries to capture the downside of that. Finally, couplers are smells that encompass code changes that exhibit unnecessary coupling. Examples of this include feature envy, where one method wishes it were another and acts as if it were another, or a middleman, where a method just coordinates the actions of other methods but doesn't actually do anything itself. Now let's take a look at a few concrete smells within Mario. First, let's take a look at an example of a long method. So I know that the level tick class is quite long, so let's take a look at that now. So here we have the tick implementation, and we can look at its major parts. So first, we can see here that we're ticking on figures, and if we scroll down, we look a little bit further, we can see that here we're going to tick on all of the items in the frame, and then finally we'll tick on the frame itself, the coin gauge and the live gauge. And this really is a lot of code, right? It starts up at line 157 and it goes all the way down to line 206, and there's a lot to understand here. And one challenge that we have is that this tick figures part in the middle really dominates the rest of this method. So while these 3 major parts are cohesive, we might want to think about trying to do something with this large tick figure segment that exists in the middle and really overwhelms the rest of the functionality in the method. Let's take a look at an example now of an OO abuser. So let's go to the mushroom class, specifically down in the hit method. So here we can see the hit implementation for mushroom, and it has this if statement where it's checking the mode. Right? So we say if mode mushroom mode.mushroom, or if mode mushroom mode.plant. And if it's a mushroom, it acts like a mushroom, right? It makes Mario grow. And if it's a plant, it actually acts like a flower, not a mushroom at all, and it makes Mario become a shooter. And what we can see here is the developer almost certainly created the mushroom class and then after a while realized they needed to add the flower functionality, but rather than making a flower class, they just added it to Mushroom themselves. So this is an example where we're checking this mode flag and varying the behavior of the implementation. And this really is an example of an OO abuser, right? The correct functionality here would really be to have this be two different classes. And we can see that in the other methods, we also are doing the same switch, right? Because we're spreading the switch, this checking for this field across the class, really it indicates that this should be a whole nother implementation. Mushroom and flower should be separate from one another. Finally, let's take a look at an example of duplicate code. So let's take a look at the constructor inside Green Turtle here. And when we're looking at the constructor, we can see that there's a lot of frame information around setting up the death frames, step up, step down, death direction, and death count. Right? There's a lot of complexity here that really has to do with rendering the view of the turtle when they die. Right? It's about the view of the turtle. And if we go and we take a look inside Spike Turtle, we can see that this same code is also here. Right? So if we changed how we wanted this to work for one turtle, we would actually have to change it for both. Right? This is duplicate code, and if we forgot to change it from one, then you'd have Green Turtle and Spike Turtle behaving inconsistently. Even though we know, because the code is the same, we want them to behave the same. Right? So this is a smell where you have this risk of not making all of the changes if you fix the code in only one place. So we want to avoid that as much as possible. And again, this would suggest a refactoring that we could look at in the future to help improve the situation. These are just 3 simple smells from a catalog of over 20. They can be a handy rubric to keep in mind when you're looking at code that seems confusing, but you aren't quite sure why. Smells are usually fixable, most commonly through refactoring.